Calculus, video 68, estimating the area under the curve, an example. So let's go through an example where we estimate the area under a particular curve. In this case, f of x is equal to 2x squared minus x, a nice parabola, on the interval 1 to 5 using 4 rectangles. And let's do first the left-hand method and then the right-hand method. So we'll do both methods here. Okay, so it's a good idea to get a picture of what's happening here, and I'll draw my best picture possible. It probably won't be to scale. F of x is equal to 2x squared minus x. Parabola opening up would have a root at 0, 0 and a root at 1/2, 0. And I would get those by letting f of x equal 0 and solving for x. Factor out the x, you get x times 2x minus 1. Solve both of those, you get x equals 0 and x equals 1/2. So some picture that looks a little bit like this. All right, so we have a parabola. It's going to cross at 0 and say 1/2. Actually, let's make it a little bit wider there. 0 and 1/2. And maybe look kind of something like this. Okay. And what we want is, go back up here, we would like what's the area under the curve. So from the curve downward to the x-axis. By the way, if that curve is below the x-axis, it would be from that curve up to the x-axis. So always towards the x-axis of this curve on the interval 1 to 5 using 4 rectangles. And let's start this one with the left hand. So we'll take the heights of the rectangles based on the leftmost point of each rectangle. So let me just kind of estimate here. Let's call that 1, and let's say 5, maybe kind of about right there. So what we're looking at is this area here. And again, I'll erase this in just a second because we're going to make it rectangles, but we are trying to estimate the area of that particular region. Okay, and it says I'd like to use 4 rectangles, so we know that the n value is 4, using 4 rectangles. So n is 4. So I'm going to draw 4 rectangles on here. And since it's the left hand, we'll take the height of the rectangle at the leftmost point of the rectangle. So I kind of start them and then based on the height, draw them from there. So the first rectangle will have a height from the leftmost point. So the height is going to be from this point there. And then for the second rectangle, the height will be at its left-handmost point, which comes from right there. The third rectangle, the height comes from its left-handmost point, which is right there. And kind of went a little bit crooked here. Let's try that again. There we go. And the fourth rectangle, the height from its leftmost point, which comes from right there. And so that last one, I'm gonna redraw that because it really doesn't go all the way up. It goes just this far. So while we're estimating the area under the curve, in this particular case, all 4 of those rectangles underestimate the actual area, right? We have extra area in here, in here, in here, and in here that we are not accounting for. So we know this will be an underestimation in this case. We'll have an underestimation. But again, thinking back to the last video, the last part of the previous video, we don't really care right now. We're going to go through this process. We're going to get an underestimation. It'll be an estimation of the actual area. But what our overall goal is we're going to let the number of rectangles go to infinity, and that's going to become more and more accurate until, well, we're going to let the number of rectangles increase, which becomes more and more accurate, and then finally letting the number of rectangles go to infinity to get the exact area under the curve. So we're okay that we're going to be a little bit off on our actual evaluation of the area here. Okay, so the n is 4 rectangles, and I need 2 things. I need the width of each rectangle, and I need the height of each rectangle, and I have arrows pointing there to the heights. Let's start though with the width. And You don't have to do this, but it makes life so much easier if you'll make all the rectangles the same width. And so we like, for the width of rectangles, to make our life easier, we'll call that delta x. And the way we find delta x, well, actually, what would delta x be in this case? What would each delta x be? Okay, if we're spanning the region from 1 to 5, that's a distance of 4, and I have 4 rectangles, we see that each delta x is equal to 1. Right, the width of each rectangle is equal to 1. And sometimes you can just look at it and be like, yeah, it's from 1 to 5, that's 4, I have 4 rectangles, it's just 1. But maybe it's more difficult. What if I said from 1 to 7 with 4 rectangles? Or from 1 to 5 with 9 rectangles? You know, how do you calculate that? The way you in general calculate this is the width of each rectangle is the b minus a. Now, what is b minus a? Remember that we started this in the last video with on an interval from a to b. So from 1 to 5 is like from a to b. An a value here is 1, a b value is 5. Okay, and so we say b minus a, that's the 5 minus the 1, divided by the number of rectangles. That will get you the width of every rectangle. In this case, that's 5 minus 1, divided by the 4 rectangles. That's 4 over 4, which is 1, which is what we found earlier. Okay, so the delta x, b minus a over n. Good to put a star on that. Remember that for maybe future problems where these aren't so easy to just figure out. So we know the width of each rectangle is 1. Now we need the height of each rectangle. So the height of the first rectangle will be the function value at the leftmost endpoint. Well, the leftmost endpoint of the first rectangle is at an x value of 1. So this first height will occur at f of 1. The next height will occur at the leftmost endpoint of the next rectangle, which will be at a distance 1 plus that delta x, which is 1, right? So this would be at 2. And then you have the next one occurs at 3, and then at 4. Because they're all 1 apart. Excuse me. So the height of the second rectangle will be at f of 2. And the height of the third rectangle will be at f of 3, the left-handmost point of the third rectangle. And the height of the fourth rectangle will be at f of 4, the left-handmost point of the fourth rectangle, which is at x equals 4, the height f of 4. All right, this is our function, f. And that's it. Now we just have to calculate the area of each of those 4 rectangles and add them together, and that will be our estimation. So let's try it. The area under the curve is approximately equal to the base of the first rectangle, that's a base of 1, times the height. The height will be at f of 1. Plus the base of the second rectangle, 1, times the height at 2, f of 2. Plus the base of the third rectangle times the height at the third rectangle, f of 3. Plus the base of the fourth rectangle times the height at the fourth rectangle, f of 4. And what are those heights, right? What is f of 1? What is f of 2? What is f of 3? What is f of 4? To do that, we go back to our function, and we plug in 1, and plug in 2, and plug in 3, and plug in 4. So to find f of 1, f of 2, f of 3, f of 4, we use f of x is equal to 2x squared minus x. So f of 1 is 2 times 1 squared minus 1. That's 2 minus 1 is 1. That's a height of 1. So what we're saying is f of 1 here, that's a height of 1. Right here. Right here. That's a height of 1. F of 2 That's 2 times 2 squared minus 2. 4, 8 minus 2 is 6. Okay, not to scale here, but f of 2, that's a height of 6. And f of 3, 2 times 3 squared minus 2, 9, 18 minus 2 is 16. So at f of 3, we get a height of 16. Definitely not to scale in my drawing. And f of 4, 2 times 4 squared minus 2. I'm sorry, I messed that one up. This one should be minus 3, and that one should be minus 4. I apologize. That makes this 15, not 16. And that would be 16, 32 minus 4, 28. So the height of the fourth rectangle would be at 28. So base times height, we get, this is equal to 1 times 1 plus 1 times 6 plus 1 times 15 plus 1 times 28, which is 1 plus 6 plus 15 plus 28. Let's see, that's 21, 22 plus 28. I am getting an answer of 50. So the left hand, I'm getting an answer of 50. So the sum of these rectangles, right? That area of the sum of the area of the rectangles is 50. In other words, the area of the first rectangle is 1. The area of the second rectangle is 6. The area of the third rectangle, 15. The area of the fourth rectangle, 28. And if you sum all those together, the sum of those four rectangles is 50, which we know is an underestimation of the actual area, because those didn't quite cover the entire area under the curve. Good. Let's try the right-hand side now. I'll try to draw the same picture again, probably not successfully. Again at 0 and say a half, and very much not to scale drawing. Again from 1 to 5. But now when I draw my rectangles, I want to use the right-handmost point. Let's do right-hand side. I want to use the right-handmost point to get the height of each rectangle. It will look something like this. Okay, so the farthest right rectangle, the fourth rectangle, if you will, I'll use the height on the right-hand side. That's way over here at the 5, the height at 5. And then we already know this is 4 and 3 and 2 and 1 there. So the third rectangle will have the height at 4, its rightmost side, and then its rightmost side for the second rectangle, and its rightmost side for the first rectangle. And you get this. And what we're going to find out here is this is an overestimation. We are overestimating for every rectangle. So we will have an overestimation here. So let's try this one out. Now, each base, so it's still 4 rectangles. The delta x is still b minus a over n. That's still 5 minus 1 over 4, which is 4 over 4 or 1. So each delta x here is still a base width of 1. The question is, what's the height? Now, the height of the first rectangle, since it's given on the right-hand side, the height of the first rectangle occurs at a function value of 2. Remember last time, the height of the first rectangle occurred at a function value of 1. In the second rectangle, it would be at a function value of 3, f of 3. In the fourth rectangle, it's here at F4. And in the fifth rectangle, it is here at F of 5. So it's going to be the same idea. I'm going to calculate the area of each rectangle with the base of 1 and a height at F of 2, then F of 3, then F of 4, then F of 5. And so the area under the curve is approximately equal to the first rectangle, base 1, height F of 2. Second rectangle, base 1, height F of 3. Right, that's this right here. Third rectangle has a height at F of 4, so plus 1 times F of 4. And fifth rectangle, a base of 1, a height at F of 5. What you'll notice is the two calculations are very similar. Go back up to the left-hand rule. It was 1 times F of 1 plus 1 times F of 2 plus 1 times F of 3 plus 1 times F of 4. The right-hand side, you don't have the first 1 times F of 1. In its place, you have at the right-hand side a 1 times F of 5. Right? There is no 1 times F of 1, and instead there's a 1 times F of 5, but the F of 2, excuse me, F of 3, F of 4 are still there. So I'm going to use a little bit of prior knowledge here and say 1 times F of 2. I already did F of 2 right up here. F of 2 is 6. So 1 times 6. And F of 3 is 15. I did that up there as well. And F of 4 is 20, I believe that was 28. Yep, 28 for F of 4. So I want to use that again. And then for F of 5, I need to figure that one out. F of 5, remembering that our F of x is 2x squared minus x. So F of 5 would be 2 times 5 squared minus 5. That is 25 times 2 is 50. 50 minus 5 is 45. So 1 times 45. So we get 6 plus 15 plus 28 plus 45. That looks to be, let's see, 15, 45, 60, 88, 94, I believe, is our overestimation. So the right-hand side was an overestimation, an area of 94. The left-hand side, an underestimation, area of 50. The actual is going to be somewhere in the middle there. Okay. So what we're saying here is the first rectangle has an area of 6. The second rectangle, 15. The third, 28. The fourth, 45. If you add all those together, you get 94. Okay. Some people like to do this where they say, okay, well, if the left-hand side in this case is an underestimation and the right-hand side is an overestimation, is the actual area kind of like an average of the two? Well, it's not. You're not going to necessarily get the actual area by averaging the left hand and right hand. You don't necessarily get the exact same overestimation in this case the right hand that we got in the underestimation for the left hand. You can find the average of the two. It will be much more accurate than either one individually, but it won't necessarily be the exact area. So if we took the left hand plus the right hand and divided it by 2 for the average, we would get 50 plus 94 divided by 2. That would be, what, 144 divided by 2 is 72. And 72 is much closer to the actual area, but it's not the actual area. When we, here in a little bit, a couple of videos, we'll find the actual area under this curve is 70 2/3. Actual area 70 2/3. 72 is much closer than, say, 94 or 50, so the average is a good thing. But I'm not worried about it. I'm not worried about these estimations being off, because while averaging them is better, then either one combined, what I want is exact area, actual area under the curve. And to do that, I'm not going to go through by averaging left hand and right hand or even using the midpoint. Instead, the best way to get actual area is to let the number of rectangles go to infinity. That's what's going to give us the actual area. So I'm not so worried about averaging the left hand and right hand to get a better approximation. I want the actual area. Okay, let's dive one more thing into this. And this next part is really important because it's going to lead us into Riemann sums, which is going to lead us into the fundamental theorem of calculus. So you'll likely have several examples where you're finding the estimated area under the curve. But let's go back to our right hand. I like using the right hand for this idea here. What I want to do is, instead of writing it out like this, like 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4, so on and so forth, I want to write it in that summation notation. Right? I want to write it like that. How can we do this in the summation notation? So basically, I'm trying to take this right here and rewrite it using sigma notation. Okay, let's see if we can do this. So kind of copy this down here. Our function was f of x is equal to 2x squared minus x. Our n is 4. We are on the interval from 1 to 5. And what I want to do is to be able to write that sum. I'll use right hand. I like right hand for this one. I want to be able to write that sum 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5 as a sum in that sum or sigma notation. So we had area is approximately equal to 1 times f of 2 plus 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5. Okay. Now the ones here, if you remember, the ones we have, this is area of a rectangle. This is the area of the base is the 1, and the base is the 1. The f of 2, the function value is the height. So this is like base times height for the area of each rectangle. The base, this 1 in this particular case, is given by the delta x value. The height is given by the function value. For the right hand, it doesn't start at the very left-hand side. It starts at, in this case, 2, which is the a value. Remember that the 1 is a and the 5 is b. This is from a to b, from 1 to 5. The function value starts not at the a value, but it starts at the right-hand side. In this case, it is at 2, which you might think of 2 as 1 plus delta x. And for the second rectangle, the height's at f of 3, which you might think of as 1 plus 2 delta x's. And then the height at 4, f of 4, is like 1 plus 3 delta x's. And the height at 5, f of 5, is 1 plus 4 delta x's. We could use that idea to rewrite the area under the curve. Instead of like this, we can say that area is approximately equal to the base, delta x, times the height at 2, plus the base, delta x, times the height at 3, plus the base, delta x, times the height at 4, plus the base, delta x, times the height at 5. Which is equal to the sum as I equals 1 to 4. So going to my summation notation, going from 1 to 4 gives me 4 rectangles. What happens when the height is 1? What happens when I is 1, I is 2, I is 3, and I is 4? That's 4 rectangles. Delta x, notice each one has a delta x in it, times f of 2. And the way I get f of 2 is I start at A plus, I add a delta x times I. Okay, stay with me here. So I've got a delta x times f of A plus delta xi. In other words, I should have probably included one. I'm gonna come back. I'm gonna write this exact thing. I'm gonna write it below it. Let me do one step first. What I can do is each term has a delta x in it, so I'm basically factoring out the delta x, leaving me with f of 2 plus f of 3 plus f of 4 plus f of 5. Right? Every term has a delta x in it. So this can be equal to the sum of delta x times f of A plus delta x times I, as I goes from 1 to 4. This is really the same thing. This is delta x times A, in our case A is 1, right, because we had the interval from 1 to 5. That's like saying from A to B. We had n value as 4 rectangles. Delta x, that's the value of 1. If you remember, delta x is equal to b minus a over n. In our case, that's 5 minus 1 over 4, which is 1. Times f of a, that's the 1, plus a delta x, that's 1, times I. So if you plug in all those things, this is delta x is 1 times f of 1 plus 1 times 1, plus delta x 1 times f of 1 plus 1 times an I value of 2 now, plus 1 times f of 1 plus 1 times 3, plus 1 times f of 1 plus 1 times 4. Again, that's just letting I go from 1 to 2 to 3 to 4. If you do that, we get 1 times f of 2, 1 plus 1 times 1 is 2, plus 1 times f of 3, plus 1 times f of 4, plus 1 times f of 5. Right. Again, I'm just plugging in the a value is 1, the delta x value is 1, and then I'm letting I range from 1 to 2 to 3 to 4. I goes from 1 to 4. And I get the sum. And so this sort of formula right here, we could use in general to find the right hand. So in general, the right hand can be found like this. It's the sum, I equals 1 to n. Notice up here I used 4 because I wanted 4 rectangles. N value of 4, 4 right there, that gives me 4 rectangles. If I wanted 8 rectangles, I would let that top value be 8. So it's I equals 1 to n of the delta x times f of a plus delta x times I. We can use that for the right hand. The left hand is very similar, but we start back where the first height occurs at A. Right, if you go way back up here, left hand, the first height of the first rectangle is occurring at that value of 1, is occurring at A. And so instead of changing everything, all we have to do is back off the I. Instead of starting at 1, have it start at 0 and ending at n minus 1. That's still n rectangles of delta x times f of a plus delta xi. But now since I is starting at 0, the first term, delta x times 0, that goes away, and all you have is f of a for your first term. Right, so that would be your left hand. Now, we're going to expand on this, and I'm going to expand on it from the right-hand side with the idea that we're going to let the number of rectangles go to infinity, as I've mentioned many times here, to get an exact area. And so it doesn't really matter whether I'm using left hand or right hand, but I like that I starting at 1 and going to n better than I like the I starting at 0 and going to n minus 1. That's the idea. We'll take and expand on that next time to talk about Riemann sums and the fundamental theorem of calculus.